Hi guys, we're doing here an example in the section on the spectrum. So we have defined at this point the resolvent set, the resolvent operator, the spectrum. We have then further partitioned the spectrum into three parts: the point spectrum, the continuous spectrum, and the residual spectrum. Our typical example is then always the same. Given here's some operator on some space, compute all these guys. All right. So far what we have done here, this is the example of the right shift. We are on Hilbert space of square summable sequences over the complex number field. We have figured out, well, the first building block, namely that there's no eigenvalues, so the point spectrum is empty. And now we are gradually moving forward, right? So first here I figured out that the spectrum itself, using the Neumann series, has to be a subset of the closed unit disk in the complex plane. And now I'm actually going to show that the spectrum is the closed unit disk. All right. So how to do? I claim here that lambda I minus r is non-invertible on the whole unit disk. Namely, at lambda equals 0, it is not invertible simply because, well, the right shift puts a 0 in the first entry of any vector in little L2, and so that means in turn this guy here, which is certainly in L2, is not in the range of the right shift. Then if lambda is different from 0 but in complex modulus less than or equal to 1, so you're inside the punctured unit disk now, then I claim that this equation here has no solution that is square summable. And once shown, this would then prove that indeed lambda I minus r is again not surjective if this constraint is satisfied. All right. But why does it have no solution? Well, if you just write out the left-hand side and the right-hand side here. So on the left-hand side, so lambda I, okay, so that means I'm writing it entry-wise now. This is the identity, so there will be in the first one will be lambda x1, and from the minus rx piece nothing comes because the right shift puts a 0 in the first entry. All right, so you have this. Then you go to the second entry, you will have lambda x2 from the lambda identity part, and then minus rx, and the right shift in the second entry has the first entry of x, so you will have minus x1, and then you continue. Lambda x3 minus x2, lambda x4 minus x3, and so on and so forth, and all of this 1, 0, 0, and like this. And what does this yellow stuff tell you? Well, if you solve it now for x, and you can because lambda is different from 0, that's how the thing is constructed, then you have x1 is 1 over lambda, then x2 is x1 over lambda, so you use the information that you already have, you get 1 on lambda squared. And then you will see this continues, xk is 1 over lambda to the power k. Yeah, but that is a geometric sequence, right? And it is not summable if lambda is less than or equal 1, because then 1 over lambda is greater than 1 in complex modulus, right? And after all, this series here, 1 over lambda, let's put here k, is divergent if lambda is outside that, no, the other way around, because it's 1 over lambda in the sum, if lambda is inside, okay? So that's why this has no solution, no square summable solution. All right, good. And that shows then indeed what we wanted. Thus, let's write it here. The spectrum of the right shift is the closed unit disk in the complex plane. All right, so the other one we highlighted in green. Let's also do this in green. Okay, good. So now, well, once you have this, of course, it's clear the resolvent set is the complement. So this is all lambdas that are in modulus strictly greater than 1, all right? So this picture up here, that is the correct one. And we already know that the point spectrum is equal to the empty set. So now we have to see how that closed unit disk is partitioned into continuous and residual spectrum. And since the union is going to be disjoint, it's sufficient to compute one part. and then once we have that, we will know what the other part is. Right? So how to do that? Well, so there's now a little bit of trickery. That's why essentially why we do adjoints in all of this. Next, you use the adjoint. We use the adjoint. And the adjoint of the right shift, we computed, it is the left shift, all right, which also satisfies, that's one of the properties. So the operator norm of the adjoint, okay, you can argue here in two ways. We know the operator norm of the left shift is 1, or you can use that general property that the operator norm of the adjoint is equal to the operator norm of the operator itself, and that thing is also equal to 1. So, okay. And I claim that the point spectrum of the left shift, aka of the adjoint of the right shift, is the open unit disk. Why is this? Indeed, let's look at the eigenvector equation. So r star x equal to lambda x, okay, for x in L2 yields, okay, so this you have to write out entry-wise, very much like we did it earlier on. So this time you just get xk plus 1 is equal to lambda xk. Because it is the left shift, right? So the left shift, it shifts everything to the left. It doesn't insert a 0 anywhere. It just suppresses the first entry and puts the second entry into that place, right? Yields this for any natural number. And so you can solve this. You get x is a multiple of the following vector: 1 lambda, lambda squared, lambda cubed, so on and so forth. All right, so the lambdas now appear with positive, non-negative exponents, unlike earlier up here in yellow where they appeared with negative exponents. All right, so in this guy, this is square summable by geometric series if and only if lambda is less than 1 in complex modulus. All right, this precisely, if you look at the L2 norm of this eigenvector x there, that's precisely going to be the geometric series. And that thing, well, converges if and only if lambda in complex modulus is less than 1, right? And so this precisely tells you that the point spectrum of the left shift, aka of the adjoint of the right shift, is the open unit disk. All right, now we use a curious corollary that we had earlier on when we were discussing those projections. So remember, in the section on projections, we had the following statement. So if you have bounded linear operator TLX, then the statement was that kernel of the adjoint and the range of T, but you have to close it up, are complementary subspaces. Okay, that's what we proved. This was, let's see, this we had up front these two equations about how the kernel of the adjoint is related to the orthogonal complement of the range and vice versa. And this here, because I just said it, this doesn't work in a general non-linear space. You need a Hilbert space because it goes through the orthogonal complement, so you need the inner product. Okay, so you have this. If you have a bounded linear operator on a Hilbert space, these two subspaces are complementary, and that's what we're going to use now. All right, but not for t equals to r, but for lambda I minus r. All right, so let's write it down now. So using this yellow piece, we have that our Hilbert space is L2, so it will be equal to the kernel and then lambda I minus r and then adjoint thereof. So remember, here in yellow we have the kernel of the adjoint of t, so t will now be lambda I minus r. All right, so we have this, and then complementary means plus range lambda I minus r and closed up. All right, and remember the rules for taking the adjoint. The mapping that sends an operator to its adjoint is a conjugate linear isometric isomorphism. So what you have here is lambda bar I minus the adjoint of R plus range lambda I minus R. Now, why am I doing this? Well, the reason is I already figured out point spectrum is empty. I know the whole spectrum, so now I have to see how it partitions into continuous and residual spectrum. And remember, for the continuous spectrum, the statement was, well, lambda is not an eigenvalue, but the range of lambda I minus R is dense in L2n. And that's why I would like to have this guy here, because if it is dense, then this means in turn, because this is these are complementary subspaces, it means in turn that this guy here has to be the zero vector space. Right? That's why this identity is so useful. All right? So we have this, and the complementary nature there says that the intersection of these two guys is, well, the zero vector space. Lambda I minus R is 0. Okay? And now take lambda in complex modulus less than or equal to 1, because we already know outside everything is in the resolvent set, so I already have this information. Then this star says the range of lambda I minus R is dense in L2n if and only if, well, that kernel there is the zero vector space. Yeah, but this means precisely lambda I minus R star is injective, right? All right, so if and only if that lambda bar is not an eigenvalue of the adjoint of R of the left shift. All right, so remember this, how the eigenvalues were defined. These were precisely the points where your guy is not injective. Right, so now here I have the equivalence of being injective. That means that lambda bar there cannot be an eigenvalue, and this is a chain of equivalences there. The range dense if and only if lambda bar is not in the spectrum of the adjoint. And that's why I computed the spectrum, because we know, we figured it out just a moment ago, that's the open unit disk. Yeah, but the open unit disk is highly symmetric, and a point is in it precisely when its complex conjugate is in it. So in turn, a point is not in it precisely when its complex conjugate is not in it. Right? So this here happens if and only if lambda is not in D10. And there we have it. Because now I read from here is dense if and only if lambda is not inside the unit disk. So what does this tell me about the continuous spectrum and the residual spectrum? Well, when I'm inside the closed unit disk, then my range is not dense, and when I'm on the boundary, then it will be dense. Right, so let's write it down. The continuous spectrum of R is, in other words, just, well, the boundary. So partial D, these are lambda in C, which is lambda is equal to 1. Okay, green. All right, and the residual spectrum is quite heavy in a sense. It's everything inside. All right, and there we have it. So now we have answered all questions. The resolvent set is outside, everything outside the closed unit disk in the complex plane. The spectrum is the closed unit disk. The point spectrum is empty. The residual spectrum is the open unit disk, and the continuous spectrum is the boundary of the disk. All right, so there we have it. Okay. Good, so this took quite a while, but now we will start developing more theory, which will, in a way, it will be theory that encodes the symmetries of the operators. So we will figure out whether operators are normal up front, and then once they are normal, so if, in particular if they were unitary or self-adjoint, then immediately we get lots of information for free, which at the moment we don't have. All right. So let's do this. So proposition let X be a Banach space. And again, by the way, by this last example, because I say here X a Banach space, you saw how the Hilbert spaces are extremely handy, because you have this stuff up there, right? Which these decompositions, these complementary subspaces that you have from the projection lemma. In general Banach spaces, you don't have this, and then spectral theory becomes much harder. Right? Let X be a Banach space and T bounded linear operator on it. Then, well, here's the topological property. So in the last example, the spectrum was the outside of the closed unit disk, so that's an open set, right? That's not a coincidence, because in general the resolvent is open. Is an open set of F. Okay. Then it's an open set. Moreover, for any lambda mu in rho T, the resolvents are, the resolvent operators are lambda T, are mu of T. They commute and they satisfy the so-called resolvent formula. Solvent formula R lambda of T minus R mu of T is equal to mu minus lambda R mu of T R lambda of T. This identity in turn tells you that these two guys have to commute, because you can just relabel your variables. The left hand side, obviously you can interchange lambda and mu because it's a difference. You can put one on the other and you have a minus sign, but if you relabel lambda and mu similarly on the right hand side, then you get this additional minus, and it tells you that these guys commute. All right, so the resolvent formula, actually, though we're not using it much here in this class, that guy is really useful, especially in my research. Looks very harmless, and in fact it is harmless. I mean, it's okay here, everything is in operators, but the only thing that this guy sort of says is, if you have, I don't know, in scalars, if you have lambda minus x 1 over minus 1 over mu minus x, if you combine the fractions, then you have mu minus lambda, lambda minus x, mu minus x, and that's, you know, kind of what's written here. So you identify this with this, because the resolvent is lambda I minus t to the power 1, and that with this, and this guy gives you that, right? So it just lifts these identities sort of in the operator setting. All right, good. So how to prove this? So first we will prove that it's open. So I will say, okay, well, how to prove that something is open? Well, you take a point inside and then you show that you can fit a whole disk still centered at this point, still inside the set. And that's what we're going to do. All right, so here's the motivation for the upcoming computations. So convergence questions aside, we have for lambda naught, that will be our point in the resolvent by the Neumann series. So we're going to look at lambda I minus t inverse. Okay, then here's a little bit of trickery. So subtract something and add it in again. lambda naught I minus t. And I'm doing this because, well, you know, since lambda naught is in the resolvent, I know precisely that this green underlined thing is invertible, right? I don't know this yet here for lambda, but I know it for lambda naught, right? So then what you do is you factor out the lambda naught I minus t inverse. And then I have an identity here. I can swap the order with a minus sign. And lambda naught I minus t inverse, and then the whole thing inverse, right? So you could convince yourselves. If you multiply this guy in there, then you get precisely, well, sort of this one. And the other one, because there's an inverse also out here, it will, you know, give you the lambda minus lambda naught. And the sign is swapped, that's why you have a minus here instead of a plus. Okay, so you have this, and now this, of course, looks very much like the Neumann series. So the first guy you don't touch, because you know that it's invertible, so you just leave it. And then the second one, remember Neumann series was this 1 minus s inverse business, so sort of here's your s, right? So that's why I write now, this is I plus n1 infinity, lambda naught minus lambda n, and lambda naught I minus t to the power minus n, because there's minus 1. Okay, but this is all completely formal. As I said, convergence questions aside, I don't know yet if those series converge. All right, so for this reason, we now define with lambda naught in the resolvent. We look at the following operator, s lambda t, which will be r lambda naught of t. So that's a bounded linear operator, because lambda naught is in the resolvent. And then identity plus n1 infinity, lambda naught minus lambda to the power n, and then the resolvent lambda naught t raised to the nth power. That means you compose it with itself n times. All right. So that's the definition, and now we have to observe if that series converges. And note that, well, it's not going to converge everywhere. It's after all a power series here, right? So this, if you think about complex analysis or real analysis, this would be a power series. Here's your variable, and well, here's the coefficient, right? So now, what can we say about the convergence? And note that the infinite series converges in operator norm, provided it doesn't converge everywhere. It converges in a disk of radius at most 1 over the operator norm of the resolvent. Okay, good. Why is this? Since, well, the operator norm is submultiplicative, so up here in the series I have my resolvent at lambda naught raised to the nth power. So if I want to estimate that operator norm, then I use that submultiplicativity property. I can pull out the n out of the norm. I get an inequality. So now all that I'm saying here is, so this guy here in red, in operator norm, right? It is less than or equal to, maybe up here, well, there is a lambda minus lambda naught to the power n. And then comes the operator norm of r lambda naught t raised to the power n. So there I use my submultiplicativity and I get this, right? So in other words, when this is true, this product here will be strictly less than 1. Well, I will say like this. It will be strictly less than delta to the n with delta quantity strictly less than 1, right? That's precisely what it says, and that's why that series converges for those lambdas, because you have geometric series that dominates it, right? So that's why that series converges for these red underlined points lambda, right? So this is a disk with center lambda naught. It's an open disk, that's going to be important. An open disk with center lambda naught and radius at most 1 over r lambda naught t. And that radius there is not 0, right? Because I have 1 over r lambda naught t. That would only be 0 if that operator norm there is infinity. But that's not, because of the definition of the resolvent set, right? Good. So for such lambda, that guy S lambda t is well defined. It's well defined, and we check that lambda I minus t times S lambda t is equal to S lambda t lambda I minus t. How do you check this? Well, remember how we checked a similar property when we proved the Neumann series, right? So this is here. This guy is a limit of some partial sums, right? So you pull the limit out, and then you do the algebra for the finite sums, and then you send that small n to infinity. This is proven exactly the same way as we proved the Neumann series, right? So that I will leave to you. And this guy is equal to the identity, okay? Hence, those lambdas are in the resolvent set, because this equation tells me here that S lambda of t is the inverse of lambda I minus t, right? If lambda minus lambda naught is less than, well, now maybe I write it like this for once, r lambda naught t, okay? And lambda naught in rho t. And that precisely tells me that the resolvent is open. Moreover, S lambda t equals to r lambda t for such lambda, right? Again, I started with a point, and now I showed that I can fit a whole disk. I started with a point in the resolvent set, and now I showed I can fit a whole disk, an open disk around it that is still in the resolvent set. So the resolvent set is open. Okay. This shows that rho of t in F is open. And since, so how to get the resolvent identity? Okay, that's super easy. So r lambda t minus r mu t is equal to what? Okay, so here a little bit of trickery. R lambda of t I multiply by the identity, but I write the identity as this. Okay, notice here, this here is equal to the identity, because the resolvent is precisely mu I minus t inverse. And you do a similar thing for the second factor, so minus r lambda t, and then here the line continues here. So lambda I minus t, and then r mu t. And now you notice that there's a few common factors that you can pull out. This and this to the left, and this to the right. So that will give you r lambda of t, r mu of t, and then what's inside? Well, mu I minus t minus lambda I minus t. And if I did everything correctly, yes, the t's go out. And then what you have inside is precisely mu minus lambda times the identity. And of course the identity commutes with everything you can pull out, right? This proves, let's write it here, r lambda t mu minus lambda r mu t. Okay, so this proves the second claim. There was this claim about that these two resolvents commute, but I already explained why this is the case. This proves the second claim after interchanging lambda with mu. That part you need to show that they commute. Okay, all right, that's it. Very nice. So we did our first example. We have our first result about resolvent set being open and the resolvent formula, and now in the next video we will do more results that will eventually help us to complete such examples faster. Okay, I will see you soon.